At this very moment, something unbelievably strange is happening inside every single atom of your body. Something so bizarre, so fundamentally weird, that even the greatest physicists who ever lived could not fully wrap their heads around it. The particles that make up your skin, your bones, your brain. Every molecule of oxygen you are breathing in right now, all of them are governed by a set of rules that defy everything you think you know about reality. These rules say that a particle can be in two places at the same time. These rules say that the very act of looking at something can change what it is doing. These rules say that two particles on opposite sides of the universe can be mysteriously connected in a way that nothing in our everyday experience can explain. These are the rules of quantum mechanics. And for over 100 years, they have been the most successful, most precisely tested, most shockingly accurate set of laws in the entire history of science. Quantum mechanics has never been wrong, not once. Every single prediction it has ever made has been confirmed by experiment, sometimes to an accuracy of 12 decimal places. That is like predicting the distance from New York to Los Angeles and being accurate to within the width of a single human hair. And yet, despite all of this success, despite the fact that quantum mechanics is the foundation upon which almost all of modern technology is built, from your smartphone to the laser in your eye surgery to the transistors in every computer on Earth, despite all of this, there is something deeply, profoundly wrong. Not with the predictions of quantum mechanics. Those are perfect. But with what quantum mechanics tells us about reality itself. Because here is the puzzle. If quantum mechanics is the fundamental law of nature, and if quantum mechanics says that particles can exist in superpositions, that they can be in multiple states at the same time, then why does none of that weirdness show up in your daily life? Why, when you look at your coffee mug sitting on the table, is it always right there, in one definite place, and never smeared across the room in some ghostly quantum haze? Why, when you open a door, does it swing one way or the other, but never both directions simultaneously? Why does the world around you look so stubbornly, relentlessly classical, when the fundamental laws that govern it are anything but classical? This is not a trivial question. This is arguably the deepest question in all of physics. And for decades, physicists have pointed to one concept as the answer. One word that gets thrown around in documentaries, in textbooks, in popular science articles, as if it magically resolves everything. That word is decoherence. You have probably heard it before. Maybe you watched a video about quantum computing and someone said decoherence is the enemy, the thing that destroys quantum information. Maybe you read an article about the many worlds interpretation, and someone said decoherence explains why the different parallel universes do not interact with each other. Maybe you looked up the famous thought experiment of the cat in the box, the one where the cat is supposed to be both alive and dead at the same time, and someone confidently told you that decoherence is the reason the cat is always either alive or dead when you open the box, never both. And here is the thing that almost nobody tells you. Most of what you have been told about decoherence is either incomplete, misleading, or flat out wrong. Not because the people telling you are lying, but because decoherence is one of the most commonly misunderstood concepts in all of modern physics. It is real. It is important. It is one of the most significant discoveries of the 20th century. But it does not do what most people think it does. It does not solve the deepest puzzle. It does not explain why you see a single definite reality. And understanding exactly what it does accomplish and where it falls short will take you closer to the beating heart of the mystery of quantum mechanics than almost anything else you could learn. That is what today's journey is about. We are going to take decoherence apart, piece by piece. We are going to build it up from the ground, starting with the very basics of what makes quantum mechanics so strange. We will explore the history of this idea, how a few brilliant physicists in the 1970s and 80s stumbled upon something that changed the entire conversation about the foundations of physics. We will look at the actual mechanism, how decoherence works in physical terms, not just hand-waving but real, concrete physics. We will examine the stunning experiments that prove decoherence is a genuine physical phenomenon, not just a theoretical curiosity. We will celebrate what decoherence beautifully and triumphantly explains, because it explains a lot. And then we will turn to the hard part, the part that most videos skip over, the part that reveals a crack at the very foundation of our understanding of reality. We will see, with perfect clarity, exactly where decoherence fails, exactly what it cannot do, and why, after decoherence has done its best, the deepest question in physics remains stubbornly, maddeningly unanswered. By the end of this video, you will understand decoherence better than most physics students. And more importantly, you will understand one of the greatest unsolved mysteries in science, the mystery of why there is a definite world at all. So settle in, because this is going to be a long, deep, extraordinary ride through the strangest corners of reality. If you are the kind of person who is curious about the deepest questions, the kind of person who does not settle for surface-level explanations, then you are in the right place. Hit that subscribe button so you do not miss what comes next. And let me know in the comments right now, before we even get started, what is your current understanding of decoherence? Do you think it solves the quantum mystery? I want to know your starting point, because I guarantee your perspective is going to shift dramatically in the next 90 minutes. Let us begin at the very beginning. To understand decoherence, you first need to understand what makes quantum mechanics different from any other theory in physics. And the key difference, the single most important feature that separates the quantum world from the classical world you experience every day, is something called superposition. Now, you have probably heard the word superposition before, and if you are like most people, you probably think it means something like a particle being in two places at the same time. That is the popular version, the version you see in magazine articles and YouTube thumbnails. But the actual concept is both simpler and far more profound than that. Here is what superposition really means. In classical physics, the physics of your everyday world, every object has a definite state at every moment. Your coffee mug is on the table. The ball is in the air. The planet is at a specific point in its orbit. At any given instant, there is one answer to the question, where is this thing and what is it doing? That is how classical physics works. Everything has a definite, single, unambiguous state. In quantum mechanics, this is not the case. In quantum mechanics, the state of a system is described by something called a wave function. And the wave function can be a combination, a sum, a superposition of multiple different possible states. Not just one state, but many states at once, mathematically layered on top of each other. Now here is the crucial part. This is not the same as saying the particle is in one state and we just do not know which one. That would be classical uncertainty, like flipping a coin and covering it with your hand. The coin is definitely heads or definitely tails. You just cannot see which one yet. Quantum superposition is fundamentally different. When a quantum system is in a superposition, it is not in one state or the other, with us just being ignorant. The system genuinely has no single definite state. The different possibilities are all present, all real in some mathematical sense, all simultaneously part of the system's description. And this is not just a philosophical claim, it has measurable consequences. Because the different parts of the superposition can interfere with each other, they can add up or cancel out, just like waves on the surface of a pond. When two waves meet and their peaks line up, they combine to make a bigger wave. That is constructive interference. When a peak meets a trough, they cancel each other out. That is destructive interference. The same thing happens with quantum wave functions. The different terms in a superposition can interfere, and this interference produces effects that are completely impossible if the system were simply in one state or the other, with us being ignorant. This brings us to the single most important experiment in all of quantum mechanics. The experiment that captures everything strange about the quantum world in one elegant setup. The double-slit experiment. Imagine you have a wall with two narrow slits in it. On the other side of the wall, there is a screen that can detect where particles land. Now, you fire particles, say electrons, one at a time, toward the wall. Each electron passes through the slits and hits the screen somewhere. You record where each one lands. After sending thousands of electrons through, you look at the pattern of hits on the screen. If electrons were just tiny little bullets, you would expect to see two clusters of hits on the screen, one behind each slit. That is what you would get if you threw tiny balls at a wall with two holes. Some balls would go through the left hole, some through the right, and you would see two piles on the other side. But that is not what happens. What you actually see is an interference pattern. Alternating bands of high and low intensity. Bright bands where lots of electrons land, dark bands where very few do. This pattern is exactly what you would see if waves, not particles, were passing through the slits. Two waves, one from each slit, spreading out and overlapping, sometimes adding up and sometimes cancelling out. This is extraordinary. Each electron goes through one at a time. There is only one electron in the apparatus at any given moment. And yet, somehow, the electron seems to interfere with itself, as if it went through both slits simultaneously. As if a single electron can be in two places at once, and the two paths can interact with each other. And here is where it gets truly mind-bending. If you try to figure out which slit each electron went through, if you place a detector at the slits to watch, the interference pattern disappears. It just vanishes. You get the boring two-cluster pattern instead. Exactly what you would expect from classical particles. The act of acquiring which path information, finding out which slit the electron actually went through, destroys the quantum behavior. For decades, this was described in almost mystical terms. The electron knows you are watching. The act of observation changes reality. Consciousness collapses the wave function. This language sounded profound, but it was deeply misleading. Because it implied that something special about human awareness, something about the act of conscious observation, was somehow responsible for the quantum to classical transition. As if the universe cares whether a human being is paying attention. As we will see. Decoherence provides a far more satisfying and far less mystical explanation for why the interference pattern disappears. But before we get there, we need to understand one more crucial concept. We need to understand what coherence actually means. When the electron passes through both slits without being detected, the two paths have a well-defined phase relationship. Think of phase as the timing of a wave. If you have two waves, their relative timing determines how they interfere. When the phases are aligned, you get constructive interference, a bright band. When they are off by half a cycle, you get destructive interference, a dark band. The precise, well-defined relationship between the phases of the two paths is what produces the interference pattern. And this precise phase relationship is what physicists call coherence. Coherence means the different parts of the superposition have a well-defined relationship to each other. They know about each other, so to speak. They can interact, they can interfere, they can produce those remarkable patterns that reveal the quantum nature of reality. When a system has coherence, it can display quantum behavior. When it loses coherence, the quantum behavior disappears. And this loss of coherence, this disappearance of the well-defined phase relationship between different parts of a superposition, is precisely what decoherence is. But I am getting ahead of myself. Let me slow down and give you one more piece of vocabulary that will make everything that follows much clearer. Physicists describe the state of a quantum system using something called a density matrix. Now, do not let that term scare you. The idea is quite intuitive. A density matrix is just a mathematical table that encodes everything you could possibly know about a quantum system. It has entries arranged in rows and columns, and the entries fall into two types. The diagonal entries, the ones running from the top left to the bottom right, represent probabilities. They tell you the probability that, if you make a measurement, you will find the system in a particular state. If you have a particle that can be either spin up or spin down, the diagonal entries tell you the probability of getting spin up and the probability of getting spin down. Then there are the off-diagonal entries. These are the interesting ones. These represent the quantum coherences, the interference terms, the phase relationships between different states. When these off-diagonal entries are large, the system is highly coherent. It can show quantum interference. It can do quantum things. When these entries are zero, the coherence is gone. The system behaves classically. It is as if the different states simply have definite probabilities, like a coin that is either heads or tails. So here is the key point. Decoherence is the process by which the off-diagonal entries in the density matrix go to zero. It is the process by which quantum coherence, the magical ingredient that makes quantum mechanics quantum, gets destroyed. When decoherence happens, a quantum superposition, which can display all sorts of weird interference effects, turns into something that looks like a simple classical mixture of possibilities. That is the executive summary. Now let us understand how it actually works. The story of decoherence begins in the early days of quantum mechanics, back in the 1920s and 30s, when the theory was first being developed. From the very beginning, there was a problem. A deep, nagging, seemingly intractable problem that the founders of quantum mechanics recognized but could not solve. This problem would eventually be given a name that has haunted physics for almost a century. It is called the measurement problem. Here is the measurement problem in its simplest form. Quantum mechanics says that systems can exist in superpositions. An electron can be both spin up and spin down at the same time. An atom can be in two energy levels at the same time. A particle can be on the left side of a box and the right side simultaneously. All of this is perfectly fine according to the mathematics. The wave function happily describes all of these superpositions, and the equation that governs how the wave function changes over time. The famous equation written down by Erwin Schrödinger smoothly and deterministically evolves these superpositions without ever selecting one outcome over another. But when you make a measurement, you always get a single, definite result. You never see the electron in a superposition of spin up and spin down. You get spin up or you get spin down. Period. One or the other. And once you get that result, the system is no longer in a superposition. It has jumped, collapsed, snapped into a single definite state. This abrupt, random, discontinuous change is completely different from the smooth, continuous evolution described by the Schrödinger equation. It seems like a completely different kind of process, governed by completely different rules. So which is it? Does the Schrödinger equation always apply? If so, how do we ever get definite outcomes? Or does the Schrödinger equation break down during measurements? If so, what exactly counts as a measurement, and what is the new rule that takes over? This is the measurement problem. And in the 1920s, the most prominent figures in physics offered an answer that essentially said, "Stop asking." Niels Bohr, Werner Heisenberg, and their colleagues in Copenhagen proposed what became known as the Copenhagen interpretation. The basic idea was that quantum mechanics applies to microscopic systems, to atoms and electrons and photons. But the measuring apparatus, the laboratory equipment, the human observer, all of these belong to the classical world. There is a boundary, a dividing line, between the quantum and the classical, and when a quantum system crosses that boundary by interacting with a classical measuring device, the wave function collapses. That is just what happens. Do not ask for a deeper mechanism. Do not ask what happens inside the measurement process. The question is meaningless. Just accept the rules and calculate the predictions. For a while, this worked, at least pragmatically. Physicists could use the Copenhagen recipe to make incredibly accurate predictions, and that was good enough for most of them. But a few deeply thoughtful people found this answer profoundly unsatisfying. If quantum mechanics is supposed to be a fundamental theory of nature, it should apply to everything, not just small things. Measuring devices are made of atoms. Atoms are quantum objects. So measuring devices are quantum objects too. There should not be any fundamental boundary between quantum and classical. The entire universe should be described by one unified quantum theory. This was the position taken by several brilliant dissenters. Hugh Everett, in his landmark 1957 thesis, proposed that the wave function never collapses. Instead, every possible outcome of every measurement actually occurs, each in its own branch of a constantly splitting reality. This was the birth of what we now call the many worlds interpretation. John Bell, the Irish physicist whose work on quantum entanglement would eventually help prove that quantum mechanics really is as strange as it seems, spent decades arguing passionately that the measurement problem was a genuine problem that deserved a genuine solution, not a prohibition against asking the question. But for a long time, these voices were in the minority. Most physicists were content with the shut up and calculate approach, using the rules of quantum mechanics without worrying too much about what they meant. And the measurement problem languished as a question for philosophers rather than physicists. Then, in 1970, a German physicist named Heinz-Dieter Zeh published a paper that changed everything. The paper was titled "On the Interpretation of Measurement in Quantum Theory," and it proposed a radically new way of thinking about why the quantum world appears classical. Zeh's key insight was this: when physicists thought about quantum systems, they typically imagined perfectly isolated systems, systems that do not interact with anything else in the universe. And for perfectly isolated systems, quantum superpositions can persist indefinitely. The Schrödinger equation preserves them perfectly. But no real system is perfectly isolated. Every real system, especially macroscopic ones like cats and measuring devices and human beings, is constantly interacting with its environment. Air molecules are bouncing off it. Photons are scattering off its surface. Thermal radiation is being emitted and absorbed. There are trillions upon trillions of tiny interactions happening every second between the system and the vast, complicated, ever-changing ocean of particles that make up its surroundings. And they realized that these environmental interactions have a profound effect on the quantum state of the system. They do not just add noise or cause heating. They do something far more fundamental. They entangle the system with its environment. And this entanglement, this spreading of quantum information from the system into the environment, destroys the coherence of the system's quantum state. It wipes out the interference terms. It makes the system look classical. This was the birth of the theory of decoherence. But Zay's paper was ahead of its time. It was largely ignored. Worse, it was actively resisted. The physics establishment in the 1970s was not ready to take the foundations of quantum mechanics seriously. The dominant attitude was still shut up and calculate, and anyone who questioned the Copenhagen interpretation was viewed with suspicion. Zay's paper had difficulty getting published and received almost no citations for over a decade. The breakthrough came in the early 1980s when a young Polish-American physicist named Wojciech Zurek took Zay's qualitative ideas and turned them into a rigorous quantitative framework. Zurek developed detailed mathematical models of how environmental interactions lead to decoherence. He calculated the rates at which coherence is lost. He identified the special states that survive decoherence, which he called pointer states. And he proposed a mechanism he called environment-induced superselection, or inselection for short, which explains why nature seems to prefer certain states over others. Zurek's work transformed decoherence from a vague philosophical idea into a precise, testable physical theory, and the results were stunning. When Zurek and others, including Eric Juice, who worked closely with Zay, actually calculated how fast decoherence happens for real physical systems, the numbers were almost unbelievable. Let me give you some examples that will make your jaw drop. Take a tiny dust particle, something about 1/100,000th of a centimeter across. A microscopic speck, barely visible to the naked eye. Now imagine this dust particle is somehow placed in a quantum superposition of two different positions, separated by a distance comparable to its own size. How long does it take for the environment to decohere this superposition, to destroy the interference between the two positions? If the dust particle is floating in air at room temperature, the decoherence time is approximately 10 to the power of -31 seconds. Let me put that number in perspective. The shortest time interval ever directly measured in any laboratory experiment is on the order of 10 to the -18 seconds. The decoherence time for a dust particle in air is 1,000,000,000,000 times shorter than that. It is not just fast, it is absurdly, incomprehensibly fast. The quantum coherence of that dust particle is gone before you could ever hope to detect it, before any conceivable technology could ever capture it. And that is just a dust particle. For larger objects, the numbers get even more extreme. A bowling ball in a room temperature environment would decohere in something like 10 to the -42 seconds. That is a number so small, it makes 10 to the -31 look positively enormous by comparison. For any macroscopic object in any normal environment, decoherence happens on timescales that are so unimaginably short that the quantum behavior of the object is destroyed essentially the instant it begins. This is why you have never seen your coffee mug in a superposition. Not because the coffee mug is too big for quantum mechanics. Not because quantum mechanics only applies to tiny things. Not because there is some magical boundary between the quantum and the classical. It is because your coffee mug is constantly bombarded by countless environmental particles, photons, air molecules, thermal radiation, each one carrying away a tiny bit of information about the mug's state, each one entangling with the mug and destroying its quantum coherence. The coherence is obliterated so fast that quantum behavior never has a chance to manifest. This was a revelation. Suddenly, physicists had a concrete, physical, quantitative explanation for why the classical world looks classical. Not because of consciousness, not because of observation, not because of some mysterious collapse process, but because of the relentless, unavoidable, overwhelmingly effective interaction between every system and its environment. But to truly appreciate what decoherence does, we need to understand the mechanism in more detail. We need to see exactly how it works, step by step. So let me walk you through it carefully, starting with a thought experiment that will make the physics crystal clear. Imagine you have a single quantum particle, let us say a photon, that can take two different paths. Call them path A and path B. After the photon takes one of these paths, the two paths come back together and the photon hits a detector screen. If the photon is in a coherent superposition of path A and path B, the two paths will interfere, and you will see an interference pattern on the screen. This is just the double-slit experiment in a slightly different guise. Now imagine that along path A, there is a tiny object, let us say a single atom, that interacts with the photon if and only if the photon takes path A. If the photon takes path B, the atom is unaffected. This atom is going to play the role of the environment. It is going to be the system that the photon interacts with. Here is what happens. Before the interaction, the total state of the system, photon plus atom, is a simple product. The photon is in a superposition of path A and path B, and the atom is in its initial state. We can write this as the photon in a superposition of A and B, multiplied by the atom in its initial state. After the photon passes through the apparatus, the situation changes. If the photon takes path A, it interacts with the atom and changes its state. If the photon takes path B, the atom is left alone. So the total state becomes an entangled state. It is the photon on path A combined with the atom in its altered state, plus the photon on path B combined with the atom in its original state. The photon and the atom are now entangled. Their states are correlated. You cannot describe the photon's state independently of the atom's state. Now here is the critical question. What happens to the interference pattern on the screen? The answer depends on the atom's two states, the altered one and the original one. If these two states are identical, if the interaction with the photon does not change the atom at all, then nothing has happened. The entanglement is trivial, and the interference pattern survives perfectly. But if the two states are different, if the interaction with the photon leaves the atom in a detectably different state, then the interference pattern is diminished. The more different the two states are, the more the interference is suppressed. And if the two states are completely distinguishable, perfectly orthogonal in the language of quantum mechanics, then the interference pattern vanishes entirely. Why does this happen? Because the interference pattern depends on the coherence between path A and path B. And the coherence now resides not just in the photon, but in the joint state of the photon and the atom together. When you look at the photon alone, ignoring the atom, the coherence appears to be gone. It has not actually been destroyed, it has been transferred. It has leaked from the photon into the correlations between the photon and the atom. The information about the relative phase between path A and path B is now encoded in the state of the atom, not in the photon alone. And this is decoherence in its purest, simplest form. The quantum coherence has not been destroyed in any fundamental sense. It has been dispersed, diluted, spread out into the larger system of photon plus atom. If you could somehow bring the atom back, undo the interaction, and recombine all the quantum information, you could, in principle, recover the interference pattern. But as long as you are looking at the photon alone, ignoring the atom, the coherence is gone. Now, scale this up. In the real world, the environment is not a single atom. It is an unimaginably vast collection of particles. When a macroscopic object, like a dust particle, exists in a quantum superposition, it interacts with trillions of air molecules every second. Each air molecule becomes slightly entangled with the dust particle. Each one carries away a tiny bit of phase information. After just a few of these interactions, the coherence of the dust particle's superposition is spread across so many environmental particles that no conceivable measurement could ever recover it. Think of it like this. Imagine you have a secret message written on a single sheet of paper. That message is the quantum coherence, the delicate phase information that produces interference effects. Now imagine you take that sheet of paper and run it through a shredder. Not just any shredder, but one that cuts the paper into billions of tiny fragments. Then you take those fragments and scatter them across the ocean. In principle, all the information is still there. If you could somehow collect every single fragment from every corner of the ocean and piece them back together perfectly, you could reconstruct the message. But in practice, the information is irrecoverably lost. It has been dispersed so thoroughly, distributed across so many pieces, that no one could ever put it back together. That is what decoherence does to quantum coherence. It does not make the coherence vanish from the universe. It spreads it across the environment so thoroughly that for all practical purposes, it is gone. And this is an important point that deserves emphasis. Decoherence is not some external force that acts on a quantum system. It is not a new law of physics. It is not something that needs to be added to quantum mechanics. Decoherence is a natural, inevitable consequence of the Schrödinger equation itself. It is what happens automatically when a quantum system interacts with a complex environment, as described by the normal, standard, everyday equations of quantum mechanics. No new physics required. No modifications to the theory. Just the relentless, unstoppable entanglement of system and environment, grinding away at quantum coherence with incredible efficiency. Now, let us look at what this means for some concrete physical situations, starting with the most famous thought experiment in all of physics. The year is 1935, and Erwin Schrödinger is frustrated. He has been exchanging letters with Albert Einstein about the bizarre implications of quantum mechanics, and he has come up with a thought experiment designed to show just how absurd the theory can be. He imagines a cat sealed inside a box along with a diabolical device. A tiny amount of radioactive material sits next to a detector. If the material decays within an hour, the detector triggers a hammer that breaks a vial of poison, killing the cat. If the material does not decay, the cat lives. According to quantum mechanics, the radioactive atom is in a superposition of decayed and not decayed after the hour is up, at least if no measurement has been made. And because the fate of the cat is entangled with the state of the atom, quantum mechanics seems to say that the cat itself is in a superposition of alive and dead. The cat is both alive and dead at the same time, existing in some ghostly combination of both possibilities, until someone opens the box and looks. This thought experiment was meant to be an argument against quantum mechanics, or at least against the naive application of quantum mechanics to macroscopic systems. Schrödinger was not claiming that cats actually exist in superpositions. He was saying that any theory that predicts such a thing must be missing something. Now let us apply decoherence to this scenario and see what happens. The cat inside the box is not an isolated quantum system. Far from it. The cat is made of trillions of atoms. It is breathing air. It is radiating heat. Photons are bouncing off its fur. Air molecules are colliding with its body. Every single one of these interactions constitutes an entanglement between the cat and its environment. Part 2. When the radioactive atom decays or does not decay, and the fate of the cat hangs in the balance, the superposition of a live cat and dead cat does not remain a clean, isolated quantum state. Instead, within an unimaginably tiny fraction of a second, the two components of the superposition become entangled with completely different environmental states. The alive cat is breathing, its heart is beating, the air molecules in the box are bouncing off a warm, living body. The dead cat is cooling, its metabolism has stopped, the air molecules are bouncing off a still, cooling body. These two environmental states are radically different from each other. They become orthogonal, meaning they have zero overlap, almost instantaneously. And once that happens, the interference between the alive cat component and the dead cat component is completely destroyed. If you trace over the environment, if you ignore all those trillions of air molecules and photons and thermal particles, the cat's density matrix becomes perfectly diagonal. It looks exactly like a classical mixture. 50% chance the cat is alive, 50% chance the cat is dead. No interference terms. No quantum weirdness, just good old classical probabilities. This is what decoherence does for the cat. It explains why you never see the cat in a superposition. Not because consciousness collapses the wave function when you open the box. Not because cats are too big for quantum mechanics. But because the cat's environment destroys the quantum coherence so fast that the superposition never manifests in any observable way. By the time you open the box, the decoherence has already happened, long ago, and what you find is a cat that, for all practical purposes, was always either alive or dead, not both. This is a profoundly satisfying explanation. It removes the mystery from the apparent quantum to classical transition. It shows that the classical world emerges naturally from quantum mechanics without any special collapse mechanism, without any role for consciousness, without any arbitrary boundary between the quantum and the classical. The classical world is not separate from the quantum world. It is what the quantum world looks like when you cannot keep track of the environment. And this is just the beginning of what decoherence accomplishes. Let me tell you about another problem it solves beautifully, one that is even more fundamental than the cat puzzle. Remember the double slit experiment. When you fire electrons through two slits without detecting which slit they go through, you get an interference pattern. When you detect which slit they go through, the interference pattern disappears. For decades, this was attributed to some mystical effect of observation. The electron knows you are watching. But decoherence gives us a completely physical, completely non-mystical explanation. When you place a detector at the slits, the detector becomes entangled with the electron. If the electron goes through the left slit, the detector clicks on the left side. If the electron goes through the right slit, the detector clicks on the right side. The detector state is now correlated with the electron's path. The detector has become part of the environment as far as the electron is concerned. And the detector does not just stop there. The detector itself is a macroscopic device. Its click involves the motion of many atoms and electrons. That information rapidly spreads to the surrounding air, the wires connected to the detector, the readout device, and eventually even the photons that illuminate the laboratory. The which path information becomes redundantly encoded in the environment, dispersed across countless particles. The coherence between the two paths is utterly destroyed, and so the interference pattern vanishes. Not because the electron knows you are watching, not because consciousness collapsed anything, but because the detector, a physical object interacting with the electron, became entangled with the electron's path information, and that entanglement destroyed the coherence needed for interference. But here is something even more remarkable. What if you could somehow erase the which path information from the detector before it spreads to the environment? What if you could undo the entanglement? This is exactly what the quantum eraser experiment does. In a quantum eraser setup, the which path information is initially recorded by some device, typically involving the polarization state of entangled photons. The interference pattern disappears, just as you would expect. But then, by performing a special measurement on the device that erases the which path information, without disturbing the electron itself, you can bring the interference pattern back. This is extraordinary. It proves beyond any doubt that the disappearance of the interference pattern is not caused by some physical disturbance to the electron. The electron is not being pushed or kicked by the measurement. What is happening is purely about information. When the which path information is available in the environment, coherence is lost and interference disappears. When the which path information is erased before it spreads, coherence is restored and interference comes back. It is information, not force, that matters. And decoherence is the process by which that information spreads into the environment. The quantum eraser is one of the most beautiful confirmations of the decoherence picture. It shows us that quantum coherence is not fragile in some mystical sense. It is fragile in a very specific, very physical sense. It is fragile because any interaction that correlates the system with its environment will spread phase information into the environment, and once that information is out there, practically speaking, you cannot get it back. Now let me tell you about some of the most remarkable experiments that directly demonstrate decoherence in action. Experiments that allow us to watch, in real time, as a quantum system transitions from quantum behavior to classical behavior. In 1999, a team led by the Austrian physicist Anton Zeilinger performed an experiment that remains one of the landmarks of quantum physics. They took molecules of carbon-60, also known as Buckminster fullerene or buckyballs, and sent them through a double-slit apparatus. Carbon-60 molecules are not small. Each one consists of 60 carbon atoms arranged in a soccer ball-shaped cage. They are large enough to be visible under an electron microscope. And yet, incredibly, Zeilinger's team observed a clear, unmistakable interference pattern. These relatively large, complex molecules were behaving quantum mechanically, displaying wave-like behavior, just like electrons in the classic double-slit experiment. This was already remarkable. But what makes this experiment truly important for our story is what happens when you increase the temperature. When the buckyballs are heated up, they start to emit thermal photons, infrared radiation. These photons carry information about the molecule's position and state. They are, in effect, miniature messengers that leak which path information into the environment. As the temperature increases and more photons are emitted, the decoherence rate increases. The interference pattern begins to fade. And if the temperature is high enough, the interference pattern disappears entirely. The buckyballs transition from quantum to classical behavior, and you can watch this transition happen smoothly and controllably by turning a dial. This experiment is decoherence made visible. It is not a theoretical prediction or a thought experiment. It is a direct, experimental observation of the quantum to classical transition, driven by the emission of thermal photons that carry Witch-path information into the environment. It is exactly what the theory of decoherence predicts, and it confirms the theory beautifully. Since then, the experiments have become even more impressive. In 2011, researchers demonstrated quantum interference with molecules containing more than 400 atoms. The race to push the boundary of quantum behavior to ever larger systems continues to this day, and every experiment confirms the decoherence picture. Larger molecules require better isolation from the environment to maintain their quantum coherence, and the decoherence rates match the theoretical predictions with impressive accuracy. There is another experiment, or rather a class of experiments, that provides equally compelling evidence for decoherence. These involve devices called SQUIDs, which stands for Superconducting Quantum Interference Devices. A SQUID is a loop of superconducting material, and at very low temperatures, near absolute zero, the current flowing through the loop can exist in a quantum superposition of flowing clockwise and flowing counterclockwise simultaneously. This is a macroscopic quantum superposition. We are not talking about a single electron here. We are talking about billions of electrons, collectively flowing in two opposite directions at the same time. This is possible because superconductors at extremely low temperatures are almost perfectly isolated from their environment. The thermal fluctuations that would normally cause decoherence are suppressed to near zero. Without those environmental interactions, even a macroscopic system can maintain quantum coherence. This is an extremely important point. The SQUID experiments prove that decoherence is not about size. It is not about mass. It is not about the number of particles. It is about the strength and nature of the interaction between the system and its environment. A SQUID with billions of electrons can behave quantum mechanically because it is isolated from environmental decoherence. A single atom floating in air behaves classically almost instantly because air molecules decohere it. What matters is not the system itself, but the system's relationship to its environment. This has profound implications. It means that in principle, there is no limit to the size of a quantum system. If you could somehow perfectly isolate a baseball from every single environmental interaction, it could, in principle, exist in a quantum superposition. Of course, achieving such perfect isolation for a macroscopic object is practically impossible. But the point is that the classical appearance of the everyday world is not a fundamental feature of reality. It is an emergent feature, arising from the particular environmental conditions in which macroscopic objects find themselves. Let me tell you about yet another way decoherence manifests in the physical world, one that goes back even further than the modern decoherence program. When alpha particles are emitted from a radioactive nucleus, they are emitted as spherical waves, spreading out in all directions simultaneously. This is what quantum mechanics predicts. The alpha particle does not come out in a single well-defined direction like a bullet fired from a gun. It comes out in a superposition of all possible directions, an expanding spherical shell of quantum amplitude. And yet, when you observe alpha particles in a cloud chamber, a device where the particle leaves a visible trail of condensation as it moves through supersaturated vapor. You never see a spherical wave. You always see a straight line, a definite trajectory, a single, well-defined path through the chamber. How can this be? This puzzle was addressed as early as 1929 by the physicist Neville Mott in what is now considered one of the very first decoherence calculations in the history of physics, even though the word decoherence did not exist yet. Mott showed that the interaction of the alpha particle with the gas molecules in the cloud chamber effectively measures the particle's position at each point along its path. Each gas molecule that the alpha particle ionizes becomes entangled with the particle's position and momentum. After just a few such interactions, the spherical wave has decohered into a collection of narrow, nearly straight trajectories. The interference between different directions has been destroyed by the entanglement with the gas molecules. So the alpha particle does not follow a classical trajectory because it has to. It follows a classical trajectory because the environment, the gas molecules, forces it to. The environment acts like a continuous series of miniature measurements, constantly monitoring the particle's position and destroying the coherence between different possible paths. The result is a trajectory that looks classical even though the underlying physics is entirely quantum. This is one of the deepest lessons of decoherence. Classical trajectories, the smooth paths that objects seem to follow in our everyday world, are not fundamental features of quantum mechanics. They are emergent, arising from the continuous monitoring of macroscopic objects by their environments. Every time you watch a ball fly through the air, every time you see a planet orbit a star, you are witnessing the outcome of decoherence, the continuous destruction of quantum coherence by environmental interactions, forcing the system into states that look classical. Now let me address another fundamental question that decoherence answers beautifully. This is the question of the preferred basis, and it is one of the most technically important aspects of the decoherence program. The basic problem is this: a quantum state can be decomposed into a superposition in infinitely many different ways. When we say the cat is in a superposition of alive and dead, we are choosing a particular basis, a particular way of splitting up the state. But mathematically, we could just as easily decompose the same state into a superposition of alive plus dead and alive minus dead, or some other completely weird combination. All of these decompositions are equally valid mathematically. So why does nature seem to prefer certain decompositions over others? Why do we always see cats that are either alive or dead, never in some bizarre superposition of alive plus dead and alive minus dead? Why is position the preferred observable for macroscopic objects rather than momentum, or energy, or some exotic combination? This is the preferred basis problem, and it is one of the deepest conceptual puzzles in quantum mechanics. Without an answer to this question, we cannot fully explain why the classical world looks the way it does. Decoherence provides a stunning answer. The key idea, developed primarily by Zurek, is called environment-induced superselection, or inselection. The basic concept is this: when a system interacts with its environment, not all states of the system are equally stable. Some states get entangled with the environment quickly and lose their coherence rapidly. Others are more robust. They survive the interaction with the environment relatively unscathed. These robust states, the ones that are stable against environmental decoherence, are called pointer states. And it is precisely these pointer states that correspond to the classical states we observe. Think of it like natural selection, but for quantum states. The environment acts as a selection pressure, constantly testing every possible state of the system. States that are fragile, that quickly become entangled with the environment and lose their coherence, are eliminated. States that are robust, that maintain their identity despite environmental interaction, survive. Over time, only the pointer states remain. The rest are washed away by decoherence. For most macroscopic systems, the pointer states turn out to be states that are well localized in position and have well-defined momentum. This is not a coincidence. Most interactions in nature, from the electromagnetic force that governs molecular collisions to the gravitational force that governs planetary motion, depend on position. When the environment interacts with a system through position-dependent forces, it preferentially monitors position. States that are well localized in position are stable because they do not get rapidly entangled with the environment. States that are spread out in position are unstable because different parts of the spread out state interact differently with the environment, leading to rapid entanglement and decoherence. This is why you always see your coffee mug in a definite position, never smeared across the room. Position-based states are the pointer states for macroscopic objects in typical environments. The environment, through its constant interactions, selects these states as the ones that survive. Everything else is destroyed by decoherence. This is one of the most beautiful results in the theory of decoherence. It shows that the classical world is not just the quantum world with the coherence removed. It is the quantum world filtered through environmental selection, with only the most robust states surviving. The classical world is the result of a kind of Darwinian process acting on quantum states, with the environment playing the role of natural selection. And this brings us to a concept that takes the Darwinian analogy even further, a concept that represents the cutting edge of decoherence research. It is called quantum Darwinism, and it was developed by Zurich as an extension of his earlier work on Ein selection. The basic idea of quantum Darwinism is this. Standard decoherence tells us that the environment destroys the coherence of a quantum system. But it does more than that. The environment does not just absorb information about the system, it copies that information. It proliferates it. It creates redundant copies of information about the system's pointer states, distributed across many different fragments of the environment. Think about how you learn about the world around you. You do not interact directly with most objects. You learn about them indirectly, through the environment. You see a tree because photons from the sun bounce off the tree and enter your eyes. The photons carry information about the tree's shape, color, and position. And crucially, the tree reflects not just one photon, but trillions of photons, all carrying essentially the same information. Your friend standing next to you sees the same tree because a different set of photons enters their eyes, also carrying the same information. A camera pointed at the tree captures yet another set of photons, again encoding the same information. This redundancy is the key insight of quantum Darwinism. The environment does not just record information about a system. It broadcasts that information, creating countless independent copies spread across different environmental subsystems. And this is why the classical world appears objective, why different observers agree on what they see. They are all accessing different fragments of the same redundant environmental record. Not all information about the quantum system gets broadcast this way. Only information about the pointer states, the states that are stable against decoherence, gets copied redundantly. Information about other, more fragile quantum states does not survive the decoherence process and is not available in the environment. So quantum Darwinism explains not just why the classical world exists, but why it looks the way it does, why it is populated by objects with definite positions and properties that everyone agrees on. Recent experiments have tested the predictions of quantum Darwinism in controlled laboratory settings, using photonic systems where the environment can be carefully monitored. The results confirm that information about certain preferred states is indeed stored redundantly across multiple environmental fragments, exactly as the theory predicts. This is an active and exciting area of research, and the coming years will likely bring even more detailed experimental confirmations. Now, we have spent a considerable amount of time celebrating the achievements of decoherence. And rightly so. It is a profound and beautiful theory that has transformed our understanding of the quantum to classical transition. But now comes the moment of truth. The part of the story that most videos leave out. The part where we look unflinchingly at what decoherence cannot do. Because, despite all of its successes, despite the elegance of its mechanism, despite the stunning experimental confirmations, decoherence does not solve the deepest problem in quantum mechanics. It does not answer the question that has haunted physics since 1926. And understanding why it fails is perhaps even more important than understanding why it succeeds. Let me remind you of the measurement problem in its sharpest form. Quantum mechanics says that a system can exist in a superposition of states. When you make a measurement, you get a single, definite outcome. The theory predicts the probabilities of different outcomes with extraordinary accuracy. But nothing in the standard mathematical framework of quantum mechanics, nothing in the Schrödinger equation, nothing in the rules of quantum mechanics as they are normally written down tells you why a single outcome occurs. The Schrödinger equation treats all components of a superposition equally. It does not single one out. It does not make one more real than the others. It preserves the superposition perfectly and forever. Now, decoherence tells us that the off-diagonal terms of the density matrix go to zero. The interference between different components of the superposition is destroyed. After decoherence, the system looks like a classical mixture, a diagonal density matrix with just probabilities along the diagonal. And at first glance, this seems to solve the problem. If the cat's density matrix says 50% alive and 50% dead, with no interference terms, then it seems like the cat really is either alive or dead, and we just do not know which one yet. Problem solved, right? Wrong. And understanding why it is wrong requires us to make a distinction that is subtle but absolutely crucial. It is the distinction between what physicists call a proper mixture and an improper mixture. A proper mixture is what you have when a system is genuinely in one definite state, but you do not know which one. Imagine a bag containing one ball that is either red or blue, but you have not looked. The ball definitely has a color. It is definitely either red or blue. You are simply ignorant of which one. If you describe this situation using a density matrix, you would write a diagonal matrix with 50% probability for red and 50% for blue. This is a proper mixture. It represents classical ignorance, the state of not knowing something that has a definite answer. An improper mixture is what you get from decoherence. It is what results when you trace over the environment, when you ignore all those environmental particles that have become entangled with the system. The density matrix you get looks identical to a proper mixture. Same diagonal entries, same zero-off diagonal entries. Mathematically, they are the same object, but physically, they represent completely different situations. In the improper mixture case, the system is not in a definite state. The total state of system plus environment is still a superposition. The cat is still alive and dead in the total quantum state of the universe. It is just that the alive and dead components are entangled with different environmental states, so when you trace over the environment, the interference terms vanish and you get a diagonal density matrix. But this does not mean the cat has a definite state. It means that the cat's entanglement with the environment hides the quantum nature of its state from local observations. This is an incredibly important distinction. The density matrix cannot tell you whether you are dealing with a proper mixture or an improper mixture. The same mathematical object describes two fundamentally different physical situations. And decoherence gives you an improper mixture, not a proper one. What this means is that after decoherence, you cannot conclude that the cat is in one definite state, and you just do not know which one. The total state of the universe still contains both components. Both the alive cat branch and the dead cat branch are still present in the global wave function. Decoherence has not eliminated either one. It has merely made them invisible to local observations. Let me put this as starkly as I can. Decoherence explains why you do not see interference between the alive and dead states. It explains why, when you observe the cat, you will not see any quantum weirdness, any superposition effects, any interference between the two possibilities. It explains why the cat looks classical. But it does not explain why you see the cat alive rather than dead, or dead rather than alive. It does not explain why there is a single, definite outcome at all. The total quantum state still has both branches. Nothing in the Schrödinger equation has selected one over the other. Nothing has made one branch more real than the other. The superposition is still there at the global level. It is just hidden from you by entanglement with the environment. This is the gap between apparent classicality and genuine classicality. The gap between looking like a classical mixture and being a classical mixture. Decoherence closes the gap in appearance, but not in reality. It solves the problem of why we do not observe superpositions, but it does not solve the problem of why we observe definite outcomes. And this is not just my interpretation. The pioneers of decoherence themselves acknowledge this. Zurek himself has written extensively about the fact that decoherence alone does not solve the measurement problem. In his technical papers, he is careful to distinguish between what decoherence accomplishes and what it leaves open. Zer, the originator of the decoherence program, was always clear that decoherence was a partial solution, not a complete one. And the Stanford Encyclopedia of Philosophy, in its authoritative article on decoherence, states explicitly that while decoherence explains why we do not observe superpositions of measurement results, it does not explain why we observe measurement results in the first place. This is worth sitting with for a moment. It is one of the most important conceptual distinctions in all of physics. And it is one that is almost universally glossed over in popular presentations. And it gets worse. Because in a deep and ironic sense, decoherence actually makes the measurement problem harder, not easier. Before decoherence was understood, the measurement problem was typically framed in terms of laboratory measurements. You have a scientist measuring the spin of an electron, and the question is why a definite outcome occurs. The problem was confined to a specific, well-defined setting, the interaction between a quantum system and a macroscopic measuring device. But decoherence reveals that measurement-like interactions happen everywhere, all the time, with no special involvement of scientists or laboratories. Every time an air molecule bounces off a dust particle, that is a decoherence event. Every time a photon scatters off a surface, that is a decoherence event. Every interaction between any system and any environment is a measurement in the decoherence sense. The entire universe is constantly measuring itself, constantly entangling its subsystems, constantly decohering. This means the measurement problem is not limited to laboratories. It is universal. It applies to every physical interaction in the universe. The question of why there are definite outcomes is not a question about a special class of interactions called measurements. It is a question about reality itself. Why does the universe have a definite configuration at all? Why is there a fact of the matter about where things are and what they are doing? Decoherence, by showing that measurement-like processes are ubiquitous, has revealed that the measurement problem is even deeper and more pervasive than anyone originally thought. So what options are we left with? If decoherence does not solve the measurement problem, what does? The honest answer is that we do not know. But we have several candidates, several different philosophical and physical frameworks, each of which offers a different way of completing the story that decoherence begins. And understanding these options is essential for understanding the current state of the debate. The first option is to take the superposition seriously and accept that all outcomes really do happen. This is the many worlds interpretation, originally proposed by Hugh Everett in 1957. In this view, there is no collapse of the wave function, ever. The Schrödinger equation is always valid, and it always produces superpositions. When a measurement is made, the universe does not select one outcome. Instead, all outcomes occur, each in its own branch of reality. The cat is alive in one branch and dead in another. You are observing the alive cat in one branch and the dead cat in another. Both branches are equally real. Neither is selected over the other. Decoherence plays a central role in the many worlds picture. It is decoherence that creates the branches. More precisely, decoherence causes the different branches to become effectively independent. Once the alive cat branch and the dead cat branch have become entangled with distinct environmental states, they can no longer interfere with each other. They evolve independently, like two separate worlds. And this is why you, as an observer in one branch, are unaware of the other branches. Not because they do not exist, but because decoherence has made them invisible to you. In the many worlds interpretation, decoherence does not solve the measurement problem by producing a single outcome. It solves it by explaining why, despite the fact that all outcomes occur, each observer sees only one. The observer does not see a superposition because decoherence has segregated the different outcomes into different non-interfering branches. Within each branch, everything looks normal, classical, as if only one outcome had occurred. The illusion of a single outcome is not produced by collapse, but by decoherence-induced branching. David Wallace, one of the most prominent contemporary defenders of the many worlds interpretation, has argued that worlds are emergent structures in the universal wave function, made well-defined by decoherence. Without decoherence, the notion of separate worlds would be vague and ill-defined. It is decoherence that gives the branches their identity, that separates them from each other. That makes them behave like distinct, independent realities. But the many worlds interpretation has its own unresolved problems. The most pressing is the probability problem. If every outcome occurs with certainty, in the sense that every branch is equally real, then what does it mean for quantum mechanics to assign probabilities to outcomes? Why does the Born rule work? Why are some outcomes more likely than others if all of them happen? This is a deep and subtle question that has generated an enormous amount of philosophical and technical literature. Various proposals have been made, from decision-theoretic arguments to arguments based on self-locating uncertainty. But there is no consensus. The probability problem remains the Achilles heel of many worlds. There is also the sheer extravagance of the ontology. The many worlds interpretation asks us to accept that every quantum measurement creates an ever-proliferating tree of branching realities, most of which we will never have any contact with. Many physicists and philosophers find this deeply uncomfortable. It seems to violate a principle of parsimony, the idea that we should prefer simpler explanations over more complex ones. But defenders of many worlds counter that the simplicity should be measured in terms of the laws, not the entities. The laws of many worlds are simpler than those of theories that add collapse, even though the resulting reality is more complex. The second option is to add something to quantum mechanics, some extra ingredient beyond the wave function that determines which outcome actually occurs. The most developed version of this approach is known as Bohmian mechanics, or the pilot wave theory, originally proposed by Louis de Broglie in 1927 and later independently rediscovered and fully developed by David Bohm in 1952. In Bohmian mechanics, the wave function is not the whole story. In addition to the wave function, there are actual particles with definite positions at all times. These particles are guided by the wave function, following a deterministic equation of motion that tells each particle how to move based on the current wave function and the current positions of all other particles. The wave function acts as a kind of pilot wave, guiding the particles through space. In this picture, the measurement problem is solved by stipulation. There is always a fact of the matter about where every particle is. The cat is always either alive or dead, not both, because the particles that make up the cat always have definite positions. And those positions determine whether the cat is in a living configuration or a dead one. The wave function may contain both branches, the alive branch and the dead branch, but the actual particles are in only one of them. Decoherence plays an important role in Bohmian mechanics by separating the branches of the wave function in configuration space. Once the alive branch and the dead branch have decohered, they occupy different, non-overlapping regions of configuration space. The actual particle configuration is in one of these regions, and the wave function in the other region, the empty branch, no longer has any influence on the particle's future motion. It is as if the empty branch ceases to exist from the particle's perspective, even though it is still there in the wave function. This gives Bohmian mechanics a notion of effective collapse. The wave function does not actually collapse, but the particles effectively ignore the decohered branches, so it is as if collapse has occurred. Decoherence provides the mechanism that separates the branches, making effective collapse possible. Bohmian mechanics has its own challenges. The most significant is the issue of non-locality. The guidance equation requires each particle to respond instantaneously to the positions of all other particles, no matter how far away they are. This non-local influence is built into the theory from the start, and while it does not allow for faster-than-light signaling, it sits uncomfortably with the spirit of relativity. Extending Bohmian mechanics to relativistic quantum field theory has proven extremely difficult, and while some progress has been made, a fully satisfactory relativistic version does not yet exist. There is also the question of why the wave function should play such a peculiar role in Bohmian mechanics. The wave function guides the particles, but is not itself guided by anything. It obeys the Schrödinger equation independently of the particles. What is the wave function, ontologically? Is it a real physical field in a very high-dimensional space? Is it a law? A nomological entity? These are open questions in the philosophy of Bohmian mechanics, and different Bohmians give different answers. The third option is to modify the Schrödinger equation itself. Maybe the equation is not exactly right. Maybe it is an approximation to a deeper, more fundamental equation that includes a built-in collapse mechanism. This is the approach taken by the Grol theory, named after its creators Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber, who proposed it in 1986. In the Grol theory, the wave function does not evolve solely according to the Schrödinger equation. In addition to the smooth deterministic evolution described by the Schrödinger equation, there are occasional, random, spontaneous collapses. Each particle has a very small probability of undergoing a spontaneous collapse at any given moment. When a collapse happens, the particle's wave function is suddenly narrowed, localized to a small region of space. The probability of collapse for any individual particle in any given second is extremely tiny, something like 1 in 10 to the 16th. For a single particle, you would have to wait about 100 million years, on average, for a single collapse event. So for microscopic systems, the GRU theory is almost identical to standard quantum mechanics. But for macroscopic objects, the situation is completely different. A macroscopic object like a cat contains on the order of 10 to the 27 particles, with each particle having a tiny probability of collapse, and with so many particles, the probability that at least one of them will collapse in any given tiny interval of time is extremely high. And because the particles in a macroscopic object are entangled with each other through interatomic forces, a collapse of any one particle effectively collapses the entire object. The result is that macroscopic superpositions are very short-lived. They collapse spontaneously, on timescales much shorter than anything we could ever observe. In the GRU theory, the measurement problem is solved by modifying the physics. The Schrödinger equation is replaced by a slightly different equation that includes spontaneous collapse. And this collapse is a real, physical process, not just an effective or apparent one. The alive cat branch and the dead cat branch do not both persist. One of them is physically eliminated by the collapse mechanism. After the collapse, the cat genuinely is in one definite state. How does decoherence relate to GUO? Interestingly, decoherence and GUO are somewhat complementary. Both suppress macroscopic superpositions, but through different mechanisms. Decoherence disperses the coherence into the environment, making it locally unobservable. GRU physically eliminates the coherence through spontaneous collapse. In practice, for most situations, decoherence happens much faster than GRU collapse. So in a GRU world, decoherence first creates effectively classical branches, and then GRU collapse physically eliminates all but one of them. The GRU theory makes predictions that differ, in principle, from standard quantum mechanics. The spontaneous collapses predicted by GRU should cause tiny violations of energy conservation, tiny heating effects, and tiny deviations from the predictions of standard quantum mechanics for carefully prepared quantum systems. Experiments are currently being conducted to look for these effects, particularly in very cold, very isolated systems where the effects of decoherence are minimized and the effects of spontaneous collapse might be detectable. So far, no such effects have been found, which means that if GRA is correct, the collapse rate and localization scale must be within certain bounds. But the theory has not been ruled out. The fourth option, which is quite different in character from the first three, is to question the assumptions that give rise to the measurement problem in the first place. This is the approach taken by the Copenhagen interpretation in its various modern forms, and by a more recent framework called cubism, short for quantum Bayesianism. In the Copenhagen interpretation, At least in its original formulation by Bohr and Heisenberg, quantum mechanics does not describe an objective, observer-independent reality. It describes the relationships between quantum systems and classical measuring devices. The wave function is not a description of what a system is, but a tool for predicting the outcomes of measurements. Asking what the wave function is, or what it represents, or what really happens between measurements, is asking questions that quantum mechanics does not answer and perhaps cannot answer. In this view, the measurement problem is not really a problem. It is a pseudo-problem that arises from trying to interpret the wave function as a description of reality. If the wave function is just a predictive tool, then the fact that it does not tell you what happens between measurements is not a deficiency. It is simply the nature of the tool. Cubism, developed by Christopher Fuchs, Rudiger Schack, and others, takes this further. In cubism, quantum states are not descriptions of physical systems at all. They are descriptions of an agent's beliefs about the outcomes of future measurements. The Born rule is not a physical law. It is a normative rule, a rule about how a rational agent should update their beliefs. In this framework, the measurement problem evaporates entirely, because there is no claim that the wave function describes something out there in the world. It describes something in the agent's head. Decoherence fits into the Copenhagen and Cubist frameworks in an interesting way. It explains why different agents performing different measurements will tend to agree on their results. It explains why the classical world appears objective, even if, at a deep level, quantum mechanics is about subjective experiences and beliefs. But decoherence does not do any fundamental work in these frameworks. Because the measurement problem is not seen as a genuine problem to begin with.